So first I'll be talking about Datalog Synthesis, the problem itself, and later on in the talk, how it connects to my actual research area of automated program repair. So let's get started. So before we look at like the syntax and semantics of Datalog, etc., let's just look at this problem. So suppose we are given a graph with like nodes and edges. Over here, like the cities representing the nodes, and we want to find all pairs of reachable nodes in this graph. So if you wanted to like whip out a C++ program that had to compute this, it would look something like this, right? So it's basically a imperative set of instructions. So you first define what your graph is, and then from that you have all these for loops, like set of instructions which tell you how to compute the reachability from the edges, from the edge matrix. But the same problem, if I had to write it down in Datalog, it would look something like this. So I would just have to define a relation, the edge relation, which is like the input. So you would have a relation edge, and I just define the relation reachable. So, and just define what reachable means. So here I'm saying that if there is an edge between x and y, then y is reachable from x, or if there is an edge between z and y, and if z is reachable from x, then y is reachable from x. So it's basically, I'm just saying that reachability is nothing but like the transitive closure of the relation edge, right? And so this is what like a Datalog program for this problem would look like. And now the output for the current input graph that we have would be something like this. So it just computes the values of the new relation that we have defined, that is the reachable relation. And we have that, okay, Zurich is reachable from Basel because there already exists an edge. And a bit more second level things like Lugano is also reachable from Basel because there is a path from Basel to Lugano, right? So these are like two different paradigms of programming. So the one that you saw on C++ example is like an imperative procedure, that is you're telling how to compute things. Rather, the one on the right side is more like a declarative programming, where you're just saying what you want to compute, and the internals of how it's being computed is kind of like left to the compiler, right? Or in this case, usually we call it like the Datalog engine. So let's be a bit more formal and precise and look at the syntax of Datalog. So a Datalog program is basically a set of rules. So the program P is basically a set of rules R1 to Rn. And these rules are made of atoms. So a rule is of something of the form A1 to An implies A0. So you have like the A0, which is like a relation or a predicate, and you read the rule in this way. So if A1 to An hold, then you infer A0. So these are something, if you have already seen in logic, these are called like horn clauses. So the rules are basically horn clauses. So let me again show it to you with an example. And atoms are basically like relations, like n-ary relations. So over here you have a relation called movie, which is like just relating the name of the movie with the genre. So like Pulp Fiction is crime, Hateful Eight is crime, and so on. And the other is starring in relation. So over here you have like Tim Roth starring in Pulp Fiction, Harvey Keitel starring in Reservoir Dogs, and so on. And the other one is like directed by, like all these movies are directed by Quentin Tarantino. So these are like atoms, and a rule using these atoms would look something like this. So a super duper movie is one which has the genre crime, has Tim Roth starring in it, and has been directed by Tarantino. So you read this rule in this form. So if the movie is like directed by Tarantino, has Tim Roth in it, and is of genre crime, this implies it is a super duper movie, right? So if you look at the kind of like the pictorial picture on the right here, so it's basically like implication from the right to left. So you have like the body which is on the right, And if all the things or all the relations on the body side hold, then you infer the head atom, that is the atom on the left side. And so over here, like all the like there are no like variables that I have in my relation. All the relations have only constants, but you can as well have variables. So over here, for example, like the title is a variable. So like each of the relation can have both constants and variables in them. So coming to the semantics, so the most common way to understand what a Datalog program is through its fixed point semantics, like that is how you compute the output from the given inputs. So it's basically an iteration of the inference rules or like the Datalog program rules until you reach a fixed point. So for example, in the edge and like finding the reachable relation from the edges of a graph, it would look something like this, right? So you have the program P, and the input is basically these edge relations. So you have an edge between A to B, B to C, C to D, and so on. And then the program, which is basically a set of rules, is these two rules that you have. Like if there is an edge between X and Y, then reachable X and Y, if and the other way around, like the transitive closure thing. So over here, basically how you now compute the output is you start off initially with just your input, that is your initial facts. So these are the facts that you have. From these facts, you now apply the inference rules to generate new facts. So this is iteration 0. You start with this and you now apply the inference rules. So by using the first inference rule, you immediately know that if there is an edge, it is also reachable. So you just have now these new additional relations or new additional tuples, and then you now take all of this whole information that you have, like the iteration 0, iteration 1 all together, and you again apply the rules to generate further new facts. And you keep on iterating until you reach a point where application of any rule does not lead to any newer facts. So in this case, like after 4 iterations, now with this whole set, if I apply any of the inference rules, I'm not able to generate any more facts. So given a Datalog program and a set of input tuples, the output tuple would be something like the output would basically be the result of this fixed point computation. So you keep on applying the inference rules until you reach a point where you're not generating any new facts or any new tuples. So if we look at like Datalog in the wild zoo, this is how the hierarchy looks like, right? So you have like a relational algebra like SQL, which is more like a query language, and Prolog. So Prolog is like a full-fledged logic programming language, which is a Turing complete language. So you can make all kind of computations in it. And Datalog sits somewhere between the two. So the good features of Datalog is, of course, it's declarative, and it does not have any side effects or does not have any like explicit control flow. But since you kind of get rid of negation and you're like restricting the syntax compared to like the full-fledged Prolog, what you get is like strong termination guarantees. So you know that your program is going to terminate, which is not the case. It's kind of an undecidable problem in Prolog. So it kind of is in between the two extremes that I've shown here. And recently, so even though Datalog was like introduced in the late 70s or early 80s, it had kind of dwindled in its popularity, but recently it has kind of resurfaced in its popularity because of a new range of applications. So I think since the early 2010s, there has been a resurgence of Datalog in applications like program analysis and like big data analytics. Because of its like very declarative nature, it's very easy to build prototypes. So you can kind of imagine how it's going to be very intuitive to build like a Datalog program which does like a point-to analysis or like a alias analysis, these kind of things on a program. And it's surprisingly quite popular even in like big data analytics, because it gives a very easy interface for the user to write ad hoc programs on top of already existing infrastructure. So SEML, which is I think now part of GitHub security, is like a kind of like a commercial tool which leverages like Datalog for program analysis and so on. And the other kind of applications are also like for example, AWS Tiros. So this is kind of like an access management system, or like access control system, which uses Datalog to make its policies and so on. And RapidNet is more for like coming up with like network configuration policies. So yeah, so recently there has been like some interest again in Datalog. And one of the things is because there are now much scalable Datalog engines. So the engines which do the computation of Datalog have improved a lot. And there are these are a few to name. So Souffle, for example, is a Datalog engine which is very specifically made for like program analysis tasks. So one of the key problems in Datalog is the problem of synthesis. So by synthesis problem, I mean is this. So you're given like a set of input tuples. So in our example, it would be like the edge relation. And you're also given us a set of like output positive output tuples and negative output tuples. So these are the output tuples that you want, that you're expecting to have, and the negative ones are the ones that you do not want to have. And the synthesis problem is, can you now generate or synthesize a Datalog program such that the program that you have generated adheres to this input-output tuples. So it's kind of like programming by example. So the examples, like the input-output tuples or the input-output examples, are the specification of the program that you want to synthesize. And the problem is to find a Datalog program which adheres to these examples, like which would work on these examples. So like if to put it a bit more formally, you want that the program on the given input is a subset of all the positive examples, and it does not generate any negative examples, right? So this in general, like synthesizing a program itself might look a bit hard, but what is Datalog? It is basically a bunch of rules, right? So if you are able to pick the right rules, you have already generated a Datalog program. So that is what I mean. So the problem of synthesizing really boils down to selecting rules. So if you have a large number of candidate rules, as in over here, for example, then the problem of synthesis is to pick the right subset of these rules such that the subset of rules that you have selected would lead to the program, like it behaves well on the input-output examples that you have. And this is an NP-complete problem. I mean, you can kind of imagine that it's a very combinatorial problem in its core. So picking the right subset such that you get a matching from the input to the output is a combinatorially hard problem. And there have been several existing techniques for Datalog synthesis. One of them is like syntax guided, which I'll talk in detail a bit about. So this problem has already or has been studied a lot even in the machine learning field. So they call it like the inductive logic synthesis problem. So there the goal is that from your training data set, you have to develop a model. So the model over there is a logic program instead of a neural net or something. So the model there is a logic program which you generate by looking at the training or like the input-output examples. And this field has also again recently gained popularity mainly because of explainable AI. So since the model that you generate over here is a logic program, So there are like clear set of rules. So the way the model is going to behave is more explainable than, for example, the neural net, which is kind of a black box. And one more technique is numerical relaxation, which also I'll come to in a minute. So syntax guided synthesis is where you like first generate a large number of candidate rules, and these rules you generate by using some kind of like heuristic syntactic templates. So you kind of have like these meta rules which say that you have like two predicates on the right hand side, where the variable which have a common variable, let's say y over here, and then you have another predicate p on the left hand side. So over here, like PRS, these are like second order variables which are instantiated with relations. So these would be instantiated, for example, with edges or with reachable and so on. And the main idea here is to like generate a large set of such candidate rules and do a syntactic search until you find the right program. So it's actually kind of a bidirectional search. So you start off with the most generic program and the most specific program. So these are again like picked up from some heuristic syntactic templates. And from these, like the most generic and the most specific, you kind of iteratively look at each of these input-output examples to converge to like your final program. And in each of these iterations, like every time you look at an input-output example, this method assumes that you have an access to the oracle. So it assumes that you already have a reference implementation of the program that you want to synthesize. And so basically in each iteration, you pick up one interesting or like one controversial input, and you ask the oracle what the output of that is. So it's and then you proceed further. So this is some kind of an active learning. So you're like interacting with the oracle while you're synthesizing the new program. And of course, there's no guarantee that the two sides will converge. So it's a bit of like, yeah, so there's no guarantee that the two sides will converge. The other technique, which is very common, or you would have had something seen something similar, is like numerical relaxation. So this is a technique where usually you reduce the problem of searching in a discrete space into an optimization in the continuous space. So you would have maybe heard of like how linear programming is much simpler than integer programming. So what you do is you convert the integer program into a linear program, solve the linear program, and then get back to the like from the real domain to the integer domain. So this is something similar over here. So the problem of searching the right candidates, of searching the right rules in a set of candidate rules, that search problem gets reduced to an optimization problem. So if you look at over here, the problem was to choose the right set of rules, right, among the set of all candidate rules. Instead of that, now what you do is you have like you convert it to an optimization problem where you have like a loss function, and this loss function basically tells that instead of picking each of these, like discretely choosing a rule or not choosing a rule, you now assign a weight, like a continuous weight from 0 to 1 to each of the rules. And the loss function basically says that these weights that you have added to the rules eventually are as close as possible to the positive examples and as far away as possible from the negative examples. So, and this can be optimized using like common techniques like gradient descent and so on. And eventually, like instead of getting what you get is like weights on each of the rules that you have. So the rules might get a weight like 0.6, 0.1, and so on. And it's now very simple to get back to the discrete problem of choosing the rules by just saying that any rule which has a weight more than 0.5, I select. Any rule which doesn't have a weight more than 0.5, I do not select. So this is how like you reduce the problem into like a continuous optimization problem. So what we want to look at is something a bit different. So this is where I come back to how like the synthesis problem is connected to my area of research, that is the automated program repair. So what we call is explanation-based synthesis and repair. So these are some of the nice things that we would like to have in our approach. So the first thing is the synthesis and repair should work on small set of input-output examples, because all the previous techniques require a large input-output example, and some of them also like access to the oracle. And the other is we do not assume any access to oracles. So we need to work on the already given input output examples and not have like access to the oracle for a new input that we feel is interesting. The third is we want to like reduce the overfitting problem. So the program that we generate needs to be as general as possible and not just be very specific to the particular input output example set that has been given. And finally, it's at a different phase. So like the approach that we want to have is like assist the developer while he's developing the program and not like synthesize the program from scratch. So the idea here is like the synthesis, even though it's interesting, it can only synthesize like simple programs. So what we would want to do is like already involve the developer while he's developing the program and assist him in repairing the program. So it's at a different phase, I would say, than the synthesis problem. So like the overall setting is something like this. So like, for example, like the main idea is that once you know something doesn't work, like once you know that there is a mistake that your program is committing, the core idea here is to really look deep into what the issue is. So for example, over here, you have a candidate program P, and on the input I, it generates the output T out, while what you're expecting is Tx, let's say, right? So there's an intersection. So there's like T out is what you got from your candidate program, which has to be repaired, and Tx is like the output that you expected. So there are some, for some inputs, the output that you would have got is not what you expected. So it's like outside the expected set of outputs. So if you have such an output, what we would want to do is like carefully inspect the rules in the program which were used in the derivation. So the rules in the program which led to this output, which shouldn't have been here. And the other one is the counter problem, which is that you have an input for which the expected output was not produced. So this is a slightly more difficult problem because you already don't have a derivation tree as such. So what we intend to do is like develop like a derivation sketch with holes in them and see if it can be filled by looking at what are the new rules or like the slightly modified rules which would fit into the holes that we have in the derivation sketch. So both of these would have like additional constraints that we accumulate, and using these additional constraints, we can pass it on to a SAT solver. So SAT solver is like a satisfiability solver. So we kind of reduce the problem of generating the right set of rules, like synthesizing the problem into a satisfiability problem. So which would eventually give us the repaired program. So basically, what we would have is like the SAT solver would tell us, okay, these are the rules P1, P4, P7, and P3, which would ultimately adhere to the input-output examples. So I think I'm already running out of time, but just to like conclude, so Datalog is kind of in a sweet spot in terms of like expressiveness and its ease to like synthesize and automatically repair. And the other key point that I would like you to take away is like, if you look closer at what went wrong in the derivation process or in in the process in which a Datalog program gave an output, then it leads to like better or most faster ways of repair and synthesis. If you're interested about this topic, please let me know. I would be glad to have a chat. Thanks.